So, hi everyone. Welcome to FOSSi Dial-Up in November. Today our guest will be Tim Edwards of eFabless. I just noticed that you can't see me, which is very nice. We are sorry for the delay for those of you that live in the time zone of GMT. We didn't notice that there was a shift of summer and winter time, and we announced everything in GMT, which was a bad idea retrospectively. So sorry for that. This is the last one for 2020. There will be another one, another couple of ones in 2021 that we will announce soon. As it was on the previous slide, please sign up to our mailing list, El Correo Libre, and you will find out more over the next weeks that we will announce there. So let's switch over to Tim. Hi, Tim. How are you doing?
All right. How are you?
Fine. Really fine. A little bit stressed, as always. But really looking forward to learn more about Magic, because I know it's a really awesome tool with a lot of changes over the last couple of years. Always nice to see that this tool is still progressing. Yeah, curious to learn more. So here's the stage. Thank you.
All right. You can get my slides up. Okay, there we go. Yes, so thank you for the introduction, Stefan. And I'm Tim Edwards. I work for eFabless, and I have been a software developer for many years with the URL opencircuitdesign.com. And what I will talk about today is a program called Magic, which I've been using for something like 25 years and programming on for that time. And this is in relationship to the Google SkyWater project, which is underwritten by Google and aims to put the SkyWater process, the 130 nanometer process, up on public repositories where everybody can use it. So why open source tools? Well, if you are listening to this presentation on FOSSi, then you at least are probably a proponent of open source hardware. It is not necessarily true that if you are using open source hardware that you are going to use open source tools to make that hardware. But it is clear that that is what Google wants, and Google is very much stressing the idea that they will make the public repository compatible with open source tools, and they encourage people to use those. And of course, open source tools is what has made the whole world of Linux what it is today. And so, and I've been working on these open source tools for many years, so I'm certainly in favor of that. Why Magic? Well, there are very few open source layout tools available, and Magic is one of them. It's the one that's been around for the longest amount of time. There is Klayout, which is a good up-and-coming layout editor, and I am very much in favor of it and look forward to its development. Since it's not my tool, I won't be talking about it today, but it's certainly one that you want to look at. And as far as doing things such as I'm talking about today for DRC, if you have more than one tool to do it, then you have more robust checks. You can use as many tools as you have to do the job. So Magic does way more than just DRC, although that is mostly what I'm going to concentrate on talking about today. But it does, for instance, GDS reading and writing. It will do device extraction and net listing. It can do LEF and DEF reading and writing. It can do wiring and routing, although its routing is not up to par with, say, what you would get from a dedicated standard cell router. And it makes nice plots like the one I have put here of a chip that we submitted to SkyWater in the early days of messing around with this PDK. If I were going to just talk about how you use Magic to do DRC for the SkyWater process, this talk would be about 2 slides long, and this would be one of them. I'm going to give you a lot more background about how Magic works and why it does things like it does. But for using it in the way that we intend for the SkyWater project, you will need to install 3 things. The first one will be Magic itself, which you can get from the GitHub repository that I have listed here. You can also get it from my website, opencircuitdesign.com. GitHub is a mirror of that. You then would want to get the SkyWater PDK from GitHub from the Google site. The SkyWater PDK contains all the files and libraries and standard formats that you need for the SkyWater process. And that includes libraries like standard cells and IO. It contains primitive device libraries and all the device models. However, if you want to use that with a specific tool like Magic, then you need to create certain files and formats that are not common, but are specific to that tool. And for that, I have this other tool that I wrote called OpenPDKs, and that is essentially a PDK installer that will take all the data from the SkyWater, Google SkyWater repo and build out the files that are needed for Magic. All of these things I suggest, because we are doing continued and recent development on all of these things, to always get these from the repository and compile from source when you can. So as I said, I have been hacking on Magic for 25 years, and I have added a lot of things to it. And here are a handful of them that I'm just going to run through quickly. But I have introduced non-Manhattan geometry into Magic. I have introduced additional graphics interfaces to the base X11, which includes OpenGL and Cairo, some output formats for plotting like PNM and SVG. I have given Magic a proper understanding of stacked contacts. I have given Magic a lot of extensions for extracting devices, because the original version of Magic only understood MOSFETs, and everything was a MOSFET. If you extracted resistors and capacitors, they were also MOSFETs, and then you'd have to go apply some kind of post-processing script to go through and clean up all of those and give you back the devices that you wanted. So all of that is internal to Magic now. I also introduced hierarchical SPICE net listing, and more recently, as in the last year or two, I have given it a proper understanding of the substrate and how to extract a substrate network. And I have put the whole thing under the Tcl interpreter, which was relatively easy to do because Magic's command line interface looks a lot like Tcl, and that is not a coincidence because John Ousterhout, who wrote Magic, is also the author of Tcl, and it was actually a fairly simple matter to revert Magic to using a Tcl interpreter. I did something different than most people were doing at the time, which is that I made Magic to be an extension of the Tcl interpreter instead of the way most people were doing it, which was to embed the interpreter into Magic. I much prefer that method. Once I had Tcl inside Magic as the underlying interpreter, then I could do all sorts of things with the interpreter language, which includes making a GUI window wrapper around the whole layout window, and then on the other hand, if you can run it without invoking any of the graphics, you could use the Tcl commands to do a lot of batch processing. And with all those Tcl commands, you can make parameterized cells that are based on Tcl procedures and will draw all of your devices automatically for you. More specifically to what I'm talking about today with DRC rules, I've added some aliases for common DRC rules so that the DRC rules, when you look at the text file, are somewhat more human readable. So common names like surround, extend, and overhang for those rules. I've added certain extensions for DRC rules that Magic was previously unable to do, which was things like wide spacing rules, angle restrictions, and maximum width rules. I've also added the idea of DRC scale factors, since originally the DRCs were in units of lambda, which I'll talk about in a minute, but are not necessarily related to any common format like nanometers. And so if you have to constantly convert between its DRC units and nanometers, what you're looking at in your Foundry documentation, then it makes it very difficult to go to the Foundry documentation and copy down all the rules. Also added the idea of DRC styles and variants, which is a very useful concept that I'll get to in a little bit. Then related to DRC is the whole idea of GDS generation rules, which are Boolean geometry operators that will generate new layers from existing layers. And I have added new operator extensions to that set that came with the original Magic to do things that it was unable to do before. And I've also added some ability of Magic to do GDS composition. So it can take a GDS file and then it can break it up into individual cells and rewrite those. So we're using that capability for compiling the SkyWater PDK, in which we take the Foundry GDS library and we break it up into individual GDS cells that we put into the SkyWater PDK, and then open PDKs can take some of those and put them back into a library. And Magic is the backbone of all of that. Also, I added some ability for Magic to understand how boundary layers and pens and labels are handled in GDS. So Magic doesn't exist in a vacuum, but there are a few other tools that are very commonly used with Magic. One of them is NetGen, which is an LVS tool. I've done a lot of development on that as well over the last, I don't know, 10 or 15 years to make that into something of a professional grade tool, such as implementing the ability to do hierarchical comparison, to do RC network comparisons, and to do device property comparisons. And I also now have the ability to compare a SPICE netlist against a Verilog netlist. This is also based in TickleTK. It's very similarly done to the way Magic is built. Another one that is done similarly with a Tickle underneath interpreter, and also very similar to Magic, is IRSIM, which is a fairly often overlooked program. I would like to talk more about it. Don't have the time to today, but I would like to mention two things about it. One is that it is able to do full chip simulations, and I was able to use it a little while ago to do static timing analysis for a SoC design for which I didn't have Liberty files, so I couldn't plug the Liberty files into a standard timing analysis tool, but IRSIM could do that, and I was able to extract good values from that. Also, IRSIM is capable of doing dynamic power estimation, and I myself at a conference and a talk a few years ago said that one of the things we were missing in the open source world was an open source dynamic power estimation tool. Well, I hadn't really thought about it, but IRSIM can do that, and this needs more looking into. So a little bit of background about Magic's database, and particularly about why it doesn't necessarily fit all that well with the way other tools, particularly commercial tools, do layout. And so first off, there's the idea of objects versus paint. So Magic's database is based around the idea that layout is being made to create masks, and masks are a simple sheet, and you put photoresist layers on it, and you're essentially painting photoresist layers on that mask where you want that layout to be. So it has incorporated that idea directly into the database. Whereas most other tools have this object idea where you would paint a rectangle and that becomes an object, and you paint another rectangle and that becomes another object, and they're all organized by binning. So Magic's database is related specifically to this idea of everything exists in a mask in a single plane. So its fundamental database unit is called a tile. It's represented by a lower left-hand point coordinate and 4 pointers to other tiles, which are the topmost tile to the right, the rightmost tile to the top, the bottommost tile to the left, and the leftmost tile to the bottom. And that description is able to completely fill a plane with tiles without overlaps and without gaps. So from the user's view, if you put down a rectangle in Magic and then put down another rectangle, say in this area, then the result that you get looks like a polygon that's been blended between those two areas. In the database, what it's done is it's taken a tile like this and then split it up into a set of tiles that are still filling the plane exactly. That database allows for very nice quick searches within the plane, And that can be done with what is an iterative search. It doesn't have to be a recursive search. So it's a 3-step iterative search. And if you want to know more about this, you can go to the Magic website on open circuit design, go to documentation and find the white paper that was written by John Ousterhout. That's probably the best way to understand it. But just a quick overview of it, if you are starting at some arbitrary point and want to find the tile at some target point, you can go follow those pointers to the other tiles. So you find the tile to the top and you keep going upward until you hit the tile that's above your target. And then you will follow the tiles to the left and follow those pointers until you reach the tile that's to the left of your target point. And then you once again go up, find the tiles to the top until you reach the tile that contains your target point. And by the way the database is constructed, that tile is always guaranteed to exist. So because of the way this database interpretation is done, Magic does things differently in a number of ways. And the most obvious way is this idea of painting and erasing. So when I do layout, I will have this little white cursor box, which I can manipulate moving around on the screen and resizing using the mouse pointer. And when I run a command, it will operate on the area within that box. So one of the simplest commands you can do in Magic is to say, do an erase operation, where I would have this square of metal, and then I put the cursor box in the middle of it and say erase, and it erases the middle of it. It's a very interesting example because in Magic, this is just like every other operation, no different at all. Whereas if you're using a tool that works in objects, then this rectangle is an object, and taking a hole out of the middle of that object is a non-trivial operation. Another thing that Magic likes to do is it likes to present a clean, simple view to the user, and that means that a lot of the complexities of layout, such as implant layers particularly, are left to be done automatically and algorithmically behind the scenes, and you don't see those layers. So for instance, here, if I wanted to draw a particular type of infet, like a LVT infet in the SkyWater process, then it's a simple matter of drawing poly over diffusion, which is how a FET is described. What that doesn't show you is that there are all these extra layers. And when I go to write out GDS from this layout, Magic will create those automatically and drop them into the layout. But I don't see them in the layout. All I see is the simple view of poly over diffusion. But it will be creating, for instance, the N+ layer that defines this as an NFET instead of a PFET, and another implant layer that will define this as a low voltage threshold transistor as opposed to a regular transistor threshold. Likewise, it draws contacts in much the same way, so that what you get is a clean view that doesn't show things like all the contact cuts. But what you're drawing when you draw a contact is an area, which is very similar in the left format to what would be called a via generate rule, and that there is an area and there is a algorithm that determines how you draw contact cuts into that area. But that way the user is not responsible for figuring out, oh, how do I draw this array of contacts into the area and make sure that the spacing and the borders and all are all correct, because all of that's done automatically and the borders and the spacing are enforced automatically. Also, Magic likes to use the idea of composite types. That's something that shows up occasionally in the Foundry definition. For instance, SkyWater defines a difference between the diffusion layer and the tap layer, even though they are both the same underlying mask layer of diffusion. That's convenient for a number of things in the SkyWater process, particularly because there are different DRC rules associated with taps as associated with diffusion in that definition. Magic goes a step further. It says, okay, I'd like to show a difference between P diffusion and N diffusion, and between P tap and N tap. So it's breaking this up into many more composite types than is typical for a Foundry process description. The positive aspect of this is that when you look at the view in Magic, it's very easy to look at a layout and say, all right, here's my region where I have all my PFET devices. Here's a region where I have all my NFET devices. It's very easy to look at the layout and see immediately what's going on. The slight downside of that is that for each of these layers, I need to define an associated contact. So I've got for 4 different types of layers, I've got 4 different types of contacts. And that means the number of layers I have to work with kind of explodes. But generally, once you get used to this concept, it's actually fairly easy to work in. Magic traditionally was based on a lambda grid, which is a concept that is related to the SCMOS technology from a long time ago. And that affects the way Magic does a lot of things, although people rarely use anything like the SCMOS rules anymore. But just for kicks, I set my grid and snapping to a 0.1 by 0.1 lambda grid. And you can do layout like this, and the DRC rules follow whatever scaling that you've done. And I'm doing a conservative layout here where the rules are much more conservative than they need to be. So my layout would be necessarily much less dense than it could be. But this is a very interesting way to do automated layout, for instance. It's not the most dense layout, but it is easier to define things automatically. And then for what I'm talking most about in this talk is that DRC is run interactively in Magic, so that if I have a piece of paint, like a little metal layer here, and I add more metal layers over here, and that layer is too close to the other one, then immediately the DRC engine will run, catch that error, and pop up a little set of little white dots here that shows that I have an error. And this is called a background DRC checker. It's not exactly background. It's not in the sense of running in a separate process or a separate thread, but it will run between commands when nothing else is happening. It will go check DRCs. If there's something, it will run the DRC checks on them. Another thing very typical of Magic is that, particularly if you're a good typist, sometimes the best way to interact with Magic is to type commands into the interpreter. So you would there's a keystroke colon, which will redirect input into the console, and then you can just type commands. And often it is just easier to work that way. I would like to stop here briefly and just bring up a view of Magic here, just a little demonstration of what Magic looks like when I'm using it for anybody who is not as familiar with it. So this is the GUI wrapper that I made in Tickle around the layout window. Here I've drawn a piece of metal 1. So to show how the DRC engine works, if I were to draw another layer right next to it and it's too close, there I just got a DRC error popping up. And if I want to find out what that error is, there are things like a menu item that tells me for DRC. But as I was saying, a lot of times it's easiest just to type commands in. So as I said, the colon keystroke will redirect to the terminal here, and then I can type in DRC Y, and it will tell me what my DRC spacing error is. Another thing I briefly mentioned was the idea of using Tickle scripts to do devices. So I have from the menu devices 1, devices 2. So if I want to create a device and have it drawn automatically for me, I can go down to, say, devices NMOS, and I get a little pop-up window that allows me to choose my width and length, and then I click on create and I get the device already drawn for me with all the DRC rules already satisfied. So going back to the presentation. So to make all this happen in Magic, it's necessary to create a technology file. Unfortunately, technology files for almost any layout tool do not use common formats. And if the Foundry doesn't support the tool, then you're going to have to be making those technology files by hand. The best reference for making technology files for Magic can be found in this URL here on Open Circuit Design. I have a full manual that gives you all the sections that need to be filled out in the technology file, although I'll go through a few of them quickly in a minute. And once you've created the technology file, the next thing to do is to create all those device generators and the Tickle procedures that show how to, that will make all of those devices automatically. So the process of onboarding a new process like the SkyWater Foundry is like this. So you start with choosing what are your drawn layers. And figuring out what the colors and patterns are for this. Usually I take something boilerplate, like one of the old SCMOS technologies from the days of submitting designs to MOSIS, and use those layers and patterns and expand them as necessary for whatever technology I'm onboarding. So drawn layers would include things like the wells, diffusion, contact types, and device types, the different types of FETs or resistors, so forth. And then of course, all your routing types like poly and metal and so forth. All of those layers will be allocated to a set number of different planes that describe the mask layers vertically. So once you've defined what are your drawn layers, everything else is a auto-generated layers, and that would include all your implant layers, contact cuts inside the contact areas, things like ID layers and boundaries. For the contact cuts, because the contact areas are supposed to be generating the cuts algorithmically, you have to do some arithmetic to figure out exactly what the size of a contact layer is going to look like in Magic, because it's not the same as a contact cut. So for instance, I would go to the SkyWater documentation and look up what are the rules for a via 3. The via size here is 0.2 by 0.2 microns. And then you've got various enclosure rules for the different metal layers on top and bottom. So I take the minimum of those. So of all the metal enclosure layers, the least amount is metal 3, which must be at least 0.06 on all sides. So my drawn contact size is going to include both the cut size and the minimum boundary, and that gives me the size of my minimum drawn contact area in Magic. And then for the remainder of the rules, I will just enforce those with DRC rules, DRC surround rules. So finishing off the tech file, I have to add all these sections for the different things that Magic can do. One of them is the DRC section. So I'll give a DRC style name and give it a scale factor. So hopefully I can write all the rules in something obvious like nanometers. Then I will write out all of the rules that I need for the process, and that ends the section. Likewise, for GDS input and output, there are two different sections. One of them tells how to read in GDS from any GDS file, including things that were created from another tool or from the vendor, and map those into all of Magic's composite layers that it likes to use. And likewise, there'll be another style called for SIF output, which is taking all of Magic's composite layers and then generating the proper GDS and all those mask layers that are automatically generated. When you see the word SIF, SIF stands for Caltech Intermediate Format. It was a file format very comparable to GDS that was popular back in the day. It isn't used much anymore. It was used when Magic was written, so you'll see a lot of references to it in Magic. But as far as this talk is concerned, you can consider SIF and GDS are essentially interchangeable. And then finally, you can add the extraction rules, which tells Magic how to extract parasitics from metals, and you'll give it all of the parasitic capacitances, parasitic resistances, and then you will tell it how to extract all the different types of devices. So you have a big list of devices and how they're described in Magic layers. So on to a full description of Magic's DRC rules. So Magic, as I said, it has an interactive DRC engine, and you can see all the DRC rules as they are checked in real time. When you're doing DRC checks, it's trying to optimize that. So if you draw something, it knows that the only changes that can have been made to DRC violations would be within a certain area or halo around what you just changed. So it will only check in that area and then update its list of errors accordingly. If you want to do batch, that indicates that you want to run all DRC rules on the entire layout. It's very easy to create a batch file in Magic. You can do something like this I have over here is a simple shell script, very simple, in which I'm just using the shell script to call Magic. I call Magic with no graphics, so -d null, and no tickle console, so -no console. I give it a tech file. I give it an input Magic file. And then I run DRC in the form of doing DRC list all y, which will give me a big dump of all the DRC errors, which I can then Either, here I'm just dumping it to standard out, or I can dump it into a file, and then I can add extra procedures to pretty print the results. There are various DRC styles and variants of those styles, and this is why I have applies the DRC rules for the metal layers. And that will prevent it from being slowed down by trying to compute DRC rules for layers that you wouldn't be concerned with. When you're working with those, of course, you can make DRC violations that you won't see because they belong in the full set. So once you do this, at some point you want to sit down and say, all right, I'm going to run the full DRC on my design. You can either do that in real time by switching the DRC style to DRC full and then running DRC check, and it'll run the full DRC check. Or you can use a batch file like I just showed. There are two types of DRC rules in Magic. One is the edge-based rules, and the other is a GDS layer type rule. I just pulled this image from the documentation for Magic. It's a complicated rule. You can go to the documentation on the tech file if you want to read up about it. But basically, as it's going through its tile plane representation, it's looking at edges between every tile and every other tile. And its DRC rules are broken up into paint rules that say if you have a layer on one side of the tile and another layer on the other side of the tile, then you're allowed to have certain set of layers within a certain distance. And that's the basic generic edge rule that it uses for all the different DRC rules of this type of edge-based rule. Common edge-based rules are what you would expect. Width and spacing are built into Magic. I found early on that when looking at some of the tech files written for Magic, they used a lot of these generic edge rules, and they were very hard to parse. They're not very human readable, so I added some additional aliases for obvious things like extend rules, overhang rules, and surround rules. Each of those tends to come in different flavors. So for instance, here in the surround rule, I would have 3 different flavors. One is called absence illegal. That means that if I have layer T1 here, it must be surrounded by T2, and it must be surrounded to the distance of dist. There's another flavor called absence OK, which means if I have layer T1, it's allowed for T2 to be completely missing, and it doesn't raise an error. But if T2 exists around it, then it must have the distance of surround out to the distance dist. And then there is a directional rule, which is commonly used for contacts, in which you're told that the layer T2 must extend beyond layer T1, but only in 2 different directions out of the 4 directions. Likewise, there's a set of rules that are based on the edge-based rules. It uses the same search to find where all the edges are, but they're not the edge rules. There are different methods used to compute these things. That includes the minimum area rule or angle restriction rules, rules that require you to have only a rectangular area, or rules that require layers to exactly overlap or not to overlap at all. And then the wide spacing rule, where you have a large layer of metal changes the distance rule to metals next to it. I have been using more and more this idea of having abstract views in Magic, in which I pull in a cell from a vendor database, say, and then present only what you would see from, say, reading the left file for that macro, which only presents metal layers. An important caveat is to realize when you're using an abstract view. For instance, I brought up this abstract view in the Magic layout, and I can draw diffusion and poly underneath it, which is obviously illegal. The obvious result from that is that you should not be using abstract views in order to do DRC, and there is a way that you can tell Magic to always use the standard view of a cell before it runs DRC. So that sort of thing will be written into a batch file so that it makes sure it's working on not on an abstract layer where you could do things like this and miss DRC rules. On the other hand, there are cases in which abstract views are almost mandatory. So especially I'm thinking of things like, for instance, the SRAM design. There are so many rules in the process that are exceptions specifically for the SRAM cell. If you try to capture them all, you can expand your tech file by a factor of 2 just to capture all those specific rules. It is much easier in that case just to have an abstract view that looks correct and shows that it's DRC clean. That abstract view then, if you go to write GDS, has a pointer to the GDS file and will just pull the GDS directly from the vendor GDS and put that into the output. So you'll get exactly into the output GDS, whatever the vendor defined for that cell. That's very useful for the SRAM cell, also for the seal ring, which again contains a lot of strange layers used strangely and will break all of the normal DRC rules. And Magic is not good at having exceptions to all these rules without defining many, many extra layers to capture those. In spite of my best efforts to update Magic, there are some unimplemented rules. Most of them are connectivity type rules, such as the same net versus different net spacing for, say, well spacing rules. Also, Magic is not good at doing per cell exceptions. And unfortunately, that's something that shows up a lot in the SkyWater process, in which they'll say this rule is valid except for this particular named cell. And likewise, it doesn't do exceptions by label tags. So you can't say, oh, I want this layer to be behaving differently in the DRCs if it has a certain label on it. But most rules that just don't fit into that edge-based rule set can be implemented using the other way of doing DRC errors, which is based on the GDS or CIF operators. So not talking about DRC here, but just how it generates the GDS in the automatic way, where it's automating the generation of layers. You have standard Boolean operators where you have layers and you can operate on them with or, and not, just common geometric operators. And then some things that aren't Boolean, but similar, like grow and shrink, or a restrictive growing per layer. And then there's this squares operator, which is how you draw the contact cuts. And that's itself a pretty complicated algorithm that determines where contact cuts go and how to draw them. I have added some new and slightly more obscure CIF operators to this. One of them is the slots rule, which is like the squares rule, except for areas that are not square, which is good for making slots in metal, but is also good for other things, including making fill rectangle. There is the bloat all operation, which is to grow into a connected area, an algorithm which defines what is the largest rectangle that you can represent in a certain layout, and then an area which grows to a minimum dimension. Since Magic does all of its output automatically, there are certain problems that are very common when you output, for instance, two cells that are catacorner to each other. You may have output layers that join at a corner, for which I have these things like bridge to cover over those areas where you might have width or spacing violations, and close where you might have little gaps that need to be closed up. There are also some special purpose operators that are sometimes useful, like net to find a net by name, or bbox and boundary to define where the cell boundary is, or to define how a boundary is supposed to be represented in GDS. A temp layer is an intermediate result. So when you're trying to create a automatically generated output layer, you want to go sometimes in steps where you will do a certain number of operations and then save that as an intermediate result, and then do further operations to create other results. There's a way then, as I mentioned, that you use these GDS layers within the DRC styles. And when you do that, everything is a temp layer. So for instance, here I'm defining a temp layer called M1 huge, in which I take all my metal and then I shrink it until small bits of metal just disappear altogether. Then I grow it back again. And what I'm left with is just the pieces of metal that are larger than a certain amount, in this case, a minimum of 1500 nanometers. And then I can do things like define a halo around that, in which I take all of the large metals, grow that a little bit, subtract out the center part of that, so I'm left with a ring, and then AND that with all material, so I can find out what all material is within a certain distance of all my large metals. And that's good for implementing a DRC rule like this, which says spacing of metal 1 features attached to and within 0.28 microns of large metal 1 is less than 0.28 microns. So this rule is broken up into 2 parts. One part is put in a CIF output section in a special style, which is called style DRC, and implements all the things specifically for DRC rules. And then over in the DRC section, I have a special DRC rule called CIF spacing or CIF max width, are the 2 most commonly used rules, in which I'm referencing not layers in Magic, but I'm referencing layers that I created in my CIF output section. So you can see what Magic is doing, even though what Magic wants to present to the user is a clean view without lots of extra boxes for different implant layers. You can see what implant layers are being made by this FOSSi command. So for instance, I go to my PDK cell generator and I ask Magic to draw me a diffusion resistor like this. If I put a box around it and then say FOSSi thick ox, which is the high voltage mask, I can see, okay, the high voltage mask is covering the area of the in-well here. Likewise, if I say FOSSi P+, I can see that, okay, there's an implant layer here that's slightly larger than the diffusion, and that defines the P region of the diffusion. And then there's another layer that Magic is auto-generating on that called diffres, which is an ID marker that declares where the resistor is for purposes of LVS. Likewise, just like you can see those layers which it's outputting when it does when it's generating GDS, you can see all the layers that it's creating for doing DRC rules. To see those, I have to set my output style specifically to that DRC style that contains the rules that it's using for DRC. Then I can say FOSSi temp layer. For instance, here I have 2 temp layers. One of them is called in-well with tap, in which I'm finding all of the in-wells that have some tap contact in them. And then I have another rule called in-well missing tap, which is actually implementing the DRC rule that I want, in which I take all layers of in-well and then I subtract off all of those that have the taps, and I'm left with all the ones that are missing taps. So with the FOSSi command, I can see either of those generated rules, either the intermediate rule in which I'm looking at in-well with tap. So here I've created 2 different resistors with the PDK, and one of them has a guard ring that has contacts in it and the other one doesn't. So if I say FOSSi in-well with tap, it highlights the area of the one that has all the contacts in it. And then if I say FOSSi in-well missing tap, then it highlights the area of the one that doesn't have the tap. And since that's the one that is put into a DRC output rule, then if I run DRC on this layout, then this is the area that's going to be highlighted. There are also 2 additional rules, CIF star higher and CIF star array, that can show you what Magic is going to do when it tries to resolve problems with interacting subcells. For instance, if I have this subcell too close to this subcell, it may not say that there's an error of in-well spacing between them. It may simply say that, oh, I'm going to go resolve that by pasting over this with an extra layer of in-well that combines those two. So apart from the basic DRC rules, here's a latchup rule in which I am trying to figure out, okay, if I have a piece of diffusion, is it close enough to a tap? There's a latchup rule in SkyWater that says all diffusion must be within 15 microns of a tap. So my temp layer for this rule is to define a region called in-tap reach. That's all the areas that are within a certain distance of the in-tap. I could grow that all out at once to the 15 microns, but then I risk having crossed over some gap in an in-well and over into another in-well, which is actually belongs to a different tap with different diffusion. So I'm going to grow this in small increments in which each time I grow it a little bit and then end it with in-well. So I make sure I'm still in the same in-well that is the tap, grow it a little bit more, do the same thing. I keep doing this until I grow that area out by 15 microns. Then I implement another temp layer rule similar to the last one I was showing, in which I say, okay, I have all my pdiff that has to be close to a tap. I take all of that and I subtract off anything that's in the area of the in-tap reach, which is what I just calculated up here. And whatever's left over is missing an in-tap. It's not close enough to an in-tap. A few notes about how SkyWater implements latchup and taps, particularly for its standard cells. All of the standard cells are defined with in-well not connected to the power rail, and the ground rail is not connected to substrate. If you want to make those tap connections to satisfy those latchup rules, you need to put down a specific tap cell which makes those connections for you. It connects the power rail to the well and it connects the ground to the substrate. There's also a difference between high density and low density taps. So if you're within 50 microns of the pad frame, you must have your tap distance as short as 6 microns. And if you're outside of that region, then your tap distance can be 15 microns. Going into yet other types of DRC rules, there are density rules. Density rules are implemented in a completely different way in Magic, and you can do that using the command sif cover. And so here I've drawn some metal 3 shapes, and I can put the box around it and type the command sif cover met3, where the type that I give to that command needs to be a GDS output type, not a Magic layer type. And it will tell me, all right, here's the cell area and here's the coverage. So I've covered 62% of that area with metal 3. Typically, you'll want to do density rules through some automated checking, because there are additional restrictions on the density rules, which say the density rules have to be checked within a window of 700 by 700 microns for the SkyWater process. And so you'll want some kind of automatic script that goes through and finds all those blocks and tiles and calculates the density for each of those and then combines those into a single density result. So for that, we'll have a batch script. And the way you get around the problem of having layout that is not dense enough is you do automatic fill pattern generation. Well, I have an experimental fill pattern generator in Magic. And the idea is that if you have some layout here with lots of gaps in between it, then after you apply that automatic fill pattern generation, then it fills that area with little fill patterns to increase the density. That style is called sif-o style waffle fill. So if you use this command, you will get the style of output that generates the masks for the automatic fill pattern generation. So this will be generating just a GDS file that contains only the fill patterns. Then you can go use a compositor to pull that back and combine that with the layout to get your layout with all the fill in it. You can also paint all the fill shapes yourself using the same rules in Magic. So there's a command called sif paint, which will go into a sif output style, find the rule, compute all those automatically generated shapes, and then paint them back into the layout as magic layers. So you'll give the command sif paint, you'll give it a GDS output rule name, and then you'll give it a magic layer where you want that rule name painted into. So by saying sif paint metal 3 fill fine on metal 3, it will paint back metal 3 fill shapes. In general, I don't recommend doing this. Fill shapes are complicated and they add a great deal to the size of a GDS file that you're creating. They also complicate the DRC, make DRC run slower. So unless you feel an absolute need to draw your own fill shapes, it's better to make use of the automatic fill pattern generation. And people who do analog design do not like fill layers drawn all on top of their sensitive analog circuits, and that's why we have something called a fill block layer. So just a caution that when you use a fill block layer, you're preventing the automatic pattern generation from running. And that means that if you use too much of the fill block layer, you can prevent the fill generation from being able to reach the minimum rule for the density. And now we get to antenna rule checking, which is yet another kind of DRC rule that needs to be checked independently of the others. So antenna rules are made because there's a problem that happens during manufacturing, in which if you have a FET gate and you have a wire connected to that, and that wire is connected up to metal layers higher than it, then during manufacturing, when you have just put down this metal layer and you have not yet gotten to the metal layers above it, then you have essentially a antenna, which this wire is just a antenna connected to nothing except the gate. And that antenna during manufacturing will be collecting charge. And if it collects enough charge, it will actually create enough of a voltage on that gate to punch through the gate and destroy the FET. So there are density rules, there are antenna rules in the PDK which say that you must have less than a certain ratio between the area of your metal wire and the area of the MOSFET gate, and that rule has to be satisfied. So that can be done in Magic. One thing you have to do before you can run the antenna checks is to extract your circuit, because Magic needs to know where the FET gates are, because this rule is specifically related to MOSFET gates and the punch through problem. And so you extract your layout, and that tells Magic where all the nets are and where all the gates are. And then you can run the command antenna check, and it will go through and find which metal layers are violating the antenna ratio rule. So here I've drawn a standard cell with a small input gate and then done a ridiculously long winding net that I'm sure will violate the ratio rule from metal to gate area. Then I run antenna check on it, and it says it's reading the extract file, building a flattened net list, running antenna checks, and then it gives me a full output. Not only does it tell me where to find these antenna rules by giving me coordinates for the gate that is in violation and the metal that's in violation, but it will tell me exactly how much, by how much have I violated that rule. If you are doing standard cell layout, you're expecting your tools to do antenna checks and antenna rule violation fixes itself. However, if you're doing, for instance, a top level layout, you may have cells that do not define diffusion areas. And so it may be that even if you are doing automatic routing on the top level, the router may not understand what the antenna rules are or when they're being violated. You can fix antenna rules manually. For instance, if you go to the devices menu in the SkyWater PDK and select an N diode, you can get a in diffusion diode, which will create a reverse bias diode between N plus diffusion and the substrate. You'll then want to connect your substrate guard ring to ground, and then you'll have your wire that is violating the antenna rule passing over that, and connect that down to the end diffusion, and that will fix the antenna rule. So there are a few things that I am intending to do with Magic in the future. The first one is obviously most necessary for the upcoming shuttle run, and so I intend to have this finished within the next week, or within this week, which is to create the batch file that does full DRC processing. And that's just a file that you can pull out of OpenPDKs and run yourself on a design, and will do the full DRC from the top, running not only all of the DRC rules, but also the antenna check rules and the density check rules. Then some further future work that I would like to get done as soon as possible. One of them is to fix the full RC extraction, because Magic's RC extraction works, but it is dependent upon the .sim file format, which is it's somewhat limited in its description of the circuit, and that affects its ability to do a complete full RC extraction. So I intend to get rid of the dependence on the .sim format and use the .ext format, which has everything that it should need to do a correct full RC extraction. Also, there was the issue that I said of having to use abstract views of cells, because sometimes the vendor layout just isn't a match for Magic, particularly if with those composite types that Magic likes to use. If you have a cell that was written by a layout tool that decided to split, for instance, contact cuts from all the stuff that was surrounding the contact, then Magic has a hard time figuring out, well, these contact cuts are of this contact type, because it doesn't see those two things in the same cell. That can be automatically handled, but it involves a lot of bookkeeping and needs to be carefully done. So there's a lot of code there that I need to write to get that to work properly. So all of this work, creating the tech file for the SkyWater PDK, is all in support of the SkyWater shuttle run. This is being underwritten by Google and will be run through eFabless. The first of these shuttle runs has a deadline of November 30th, and submissions will be made to efabless.com. If you go to efabless.com now, you can find a link to the Google SkyWater stuff where you will be able to submit a project. The rules of this game are that all your projects have to be open source and put into an open source public repository. And all projects need to fit within this chip that we've designed at eFabless called the Caravelle. It's a harness chip in which we hope that the user, well, the idea is that the user should not have to deal with IOs and other aspects of how to test their designs, but all of the stuff should be done for them. And so all they need to do is build a circuit that does not involve pad frame or anything like that. And then they can drop it into this harness chip in what we have as a user area and submit that whole design. All of the pre-checks for that, for DRC rules and things, will be done with Magic using this script that I am going to be doing this week. So the Caravelle chip, this is not the full Caravelle chip, but just a mock-up of the pad frame, and all the polka dots here are where the bump bonds are on the top of it. And you have a management area which contains a RISC-V processor, and you can use that to hook into any digital circuits you have in the user project and read off values using the processor and talking to a host computer off of your project board. And then you have over 10 millimeters squared to put in a user project of any kind. So that's the Caravelle harness chip, and we are hoping that as many people as we can get to participate will join and create designs and put them into this Caravelle harness chip and submit them for the shuttle runs. And if you miss the November 30th deadline, there will be more shuttle runs coming. So we are working on all these developments of the tools, trying to get everything working in time and the harness chip to be ready. And we hope that we'll get as many people as we can, and we thank everybody who is participating in that. So that is essentially my talk on Magic, and I hope that you have learned something about Magic that you didn't know before, and will be able to use it in the future and use it for this Google project. Thank you very much for listening. Back to you, Stefan. Yes, I can. Ah, Okay, sure. Yeah, so there are 3 DRC styles that I typically put into a PDK, and I will tend to define them as being fast, full, and routing. And the full DRC will run all DRC checks. And that works fine if you're working with a small design, like a small analog layout, and you want to see all the rules all the time. You can do that with the full DRC rule deck and not see any kind of lag going on between your layout and the DRC checker. However, once the layout gets to a certain size, there will be noticeable lag, which is why I've introduced the DRC fast variant style. And that will check only the basic rules without going into the rules that are either obscure or take a lot of computation time. And that way you can have the DRC checker keep up with what you're doing without noticing lag until you get to, say, full chip designs. So if you're doing something like power routing on a full chip, or doing fixing routing on a standard cell layout, then you can switch to DRC routing, and that will check only the metal rules. And so once again, the DRC checker can keep up with what you're doing in layout. And of course, when you're using those fast and routing, you're not checking all DRC rules, so you have to be aware that at some point you want to go back to the DRC full and run a full check on your layout to catch all of the rules.
Okay, thank you very much. Sorry for the inconvenience. I was trying to stop you, but then I noticed you can't hear me. But now it's fine.
Nope, yep, sorry about that.
But it went fine in the end. I just recovered the audio and everything was fine. We have a question from Matt. He's asking, I'm not sure if you answered it already, if you can comment on generating implant layers during custom design, not for standard cells, and how you can ensure that implant width and spacing DRCs are not violated.
Well, that's a very complicated question to answer, but let me find an appropriate layer. Yeah, so generally what you'll do is make DRC layers that are a sort of composite of the drawn layers and the implant layers. So for instance, if there is a DRC rule that says that N plus layer must be a certain distance from another diffusion layer, then I will simply say, oh, diffusion must be the right distance from another diffusion layer, but then I'll add that extra or subtract that extra distance from the rule to get the exact rule for that layer. It's not always possible to perfectly describe all the rules, and so describe all DRC rules related to those implant layers, but that's why you have these GDS type rules. So you can always simply pre-calculate in your GDS section that all those layers and then check those layer distances against the layers you have in your layout. So if you want, you can actually implement all of those DRC rules directly and have the errors show up immediately.
Okay.
I prefer the combined rules. Generally, they're easier to do. Anytime you can get an edge-based rule, it's more efficient than if you have to go to one of these GDS layer-based rules.
Oh, I see. Okay, I hope that answered it. There's another question that is that Magic used to work with SCMOS rules used by Moses, and the TSMC 180 process was compatible with it. How does it work with SkyWater 130 nanometer? Is the DRC rules, are they lambda based?
No, and I haven't been doing lambda-based rules for some time. Let's see, I had a picture of that. Yeah, here. So you can, as I said, SCMOS rules were designed to be convenient to draw layout in by being in very coarse increments. Like in this case, I was doing something in 0.1 by 0.1 unit grid. So all the rules, if you stick to those dimensions, have to be somewhat more conservative, and your layout is less dense than you could make it if you followed vendor rules. But it's a lot easier to do layout this way, particularly if you're just drawing individual mask layers as opposed to using the devices from the PDK.
Mm-hmm.
But yes, it can do, it's still very much based on the lambda grid and can do that kind of layout quite conveniently.
Okay. Someone is asking what the grid size is for SkyWater.
Oh, well, what I do for a default is to use a grid size of 0.01 micron, which is twice the minimum manufacturing grid. I do that because it's easier to write rules when everything is on a factor of 10. And then I usually, in my startup script for Magic, I will divide down the Magic's internal grid by a factor of 2 so that its internal grid matches the minimum manufacturing grid.
Nice. Someone has been asking about the slides, if you can share the URLs for them in the end. Maybe we can put them in the YouTube links if you.
Oh, yes, absolutely.
Thank you very much. I think many people have to post-digest some of the things. I'm wondering, you have been doing this for a long time now. Was it mainly you, or do you see some influx of other developers contributing to the design, to Magic, or is it mainly you doing it?
It's mainly me, although occasionally I get people who are contributing things. At least by now, by having this thing up in GitHub, it's easy now for people to pull the whole repo and to give me a pull request back if they want to make changes. But it is a huge program, and it is definitely very daunting to go through it and learn how it's doing something. I did have somebody request a while ago that I should do a webinar just on how Magic's code works and how you can hack it, which would probably be like a multi-part seminar to cover everything because there's so much in there.
So it's like a job training, right? You have like 2 months of Magic source code walkthroughs then.
Yes, absolutely.
Interesting. Because you said there's a few things missing, and some of them seem a little bit like more pressing than others. Is there any area where you would suggest people that are really willing to go to the path to really learning Magic and the source code and contributing? What might be interesting to pick up as first tasks?
Well, I do have a to-do file somewhere in the code base. So I believe that's in the top level of the code. If you look at the file to-do, you'll find a long list of things that need to be done. Now, whether any of them are good for starters, I don't remember off the top of my head. If anybody wants to just ask me by submitting an issue to the GitHub issue tracker, just say, what can I do to help? And I can, I guess, provide a list of things that are easy enough for a beginner to try to get into.
Awesome, thank you. I think that's probably kind of important to highlight that people can also contribute if they want to, not only use it. I assume you're always open to bug reports and
I get on bug reports as fast as I possibly can. And I try to do, I notice a lot of repositories, they are maintained by groups of people who form these little cliques, and they are not very open to other people submitting things. I try to be as open as I can. If you submit something and it doesn't obviously mess up the entire program, I'm fairly generous about trying to get that into the code base.
Awesome. I think that's great to hear. Yeah, it's a pretty interesting area, but something, I think you really need to get into the code base probably to even understand what you're doing, right? But really interesting, really nice. Thank you very much. Just looking up. Oh, there's a question that just came in. You mentioned K-layout and that you want to see that to be used in the future. Could you elaborate on the future of the future plans with Magic and K-layout?
Well, K-layout has recently been doing a lot of development with DRC rules, and I see it as a very good way to have two checks from two different sides, from two programs that are doing things very differently. I think that's a very good way to catch errors that one may not be able to do or one may be doing wrong, and to find bugs and things like that. So I certainly want to be able to use that. I have not done enough testing with it to be able to vet it properly for the SkyWater process, at least not for now. That's something I want to do in the near future.
Awesome. Thank you very much.
Okay, thank you.
Oh, there's another question. Let me just check there. Some questions coming in now. For complex Magic layout that gets generated at the end of the open lane flow, how can they select the N-well and P-well through the TCK on window? Sorry.
Well, if you have, once you get a layout in from OpenLane, you can read it back as a def file. I forget whether OpenLane actually generates a magic file out of it or not, but certainly you can read the def file back. Then if you want to look for the connectivity through a certain net, you can do there's a select thing in which you type S to select a object like this. I just selected a contact. If I press S again in the same space, it will highlight everything connected to that. Sometimes, depending on the complexity of the net, you have to do that 3 times. So that's why I said select will get you the full net. And that's how I trace connectivity through like power, ground, or through networks where you think there might be a short or an open.
Okay, nice. I hope this answers the question. As there are no other questions, I want to thank you very much again. I think it was a real pleasure. It was a good roundup of the first series of FOSSi Dial-Up. As I announced in the beginning, there will be a short break in December for holiday season, and we will be back in January with a new program. I'm pretty confident that there will be more talks around SkyWater PDK and hopefully many success stories that we will see. Looks very promising. I'm really looking forward. Just check the deadline. Pretty sure I can't make it currently, but I hope for another shuttle run. And yeah, everyone, please subscribe to our newsletter so that you can get the regular update. Check the website, and we will be back in January. We already have a few speakers confirmed. We will set up the schedule soon. Yeah, Tim, thank you very much. Really great. Keep up the good work for another. What is it? How long did you do it now? Open circuit design.
At least 25 years.
Okay. So let's start the next 25, right?
Right.
Awesome. Then have a good day. Bye.
All right. Thank you. Bye-bye.